Health. That's in West Ballroom A and B. The booklet printing was wrong. But this is interpretable comparison of distributions and models. And we'll have 3 speakers. It'll be divided into 3 sub-sessions of about 35 minutes each. And our first speaker is going to be Arthur Cretin.
So thank you for coming and welcome to the tutorial. So it's, as Jasper said, a tutorial on interpretable comparisons of distribution and models. So we have 3 speakers. I'll speak first, then Douglas Sutherland, and then Witawat Cretin will be the final speaker. So just to give a sort of overarching theme of the talk, we're going to be looking at 2 sort of broad classes of problems. So here's the first class of problem. Okay, I have 2 samples. I have 2 sets of objects from 2 distributions P and Q. So in this case, one of my sets of objects is a set of dogs. The other set of objects is a set of fish. And my task here is to tell, based on these sets of observations drawn from these distributions, whether the distributions are the same or not. Okay, I see the observations. I need to conclude something about the underlying distributions. So this is one of the themes we'll be looking at. The second theme is I have a set of objects and I have a model. Okay, so here I have a set of images of dogs from some distribution generating dogs. And then I have a model. It might be an implicit model like a GAN. It might be an explicit model. So I might have explicitly a form of the probability of these observations. And my task here is to tell whether, how good is my model? And if it's going wrong, where is it going wrong? Okay, so the 2 tasks, comparing 2 sets of samples or comparing samples to model. And in both cases, what we're interested in is not only to draw a conclusion, like, are our samples different, but ideally we want to understand why we've drawn our conclusion. So why is it that my samples of fish are different from my samples of dogs, or where is it that my model is going wrong? Okay, to give a concrete example, here's a nice example of a generative adversarial network. In this case, you've got on the left handwritten digits by a human, on the right handwritten digits by a computer. So this is a slightly older paper, so they were still working on MNIST. And according to the paper, when they used Amazon Mechanical Turk to try and tell whether the digits were real or fake, humans were performing at chance level. So this is pretty hard. Like, obviously, the GAN is good enough that it's fooling a human sort of most of the time. This is an example we're going to revisit because it's actually, using some of the tools we'll develop, reasonably easy to tell the fake from the real digits. Okay, so there will be ways to find out why they're different and to understand that they're different. Okay, so that's the theme. So to give now a little bit of an outline of how we're going to do this presentation, I'll talk about divergence measures just in the abstract. I'll talk about integral probability metrics and also phi divergences. Phi divergences, you might have heard of them also in the form of F divergences or Ali-Silvi divergences. I will use phi divergences for notational reasons that might become clear later. What we're going to do then is have Dougal speak about statistical hypothesis testing. So if I have a distance, is it large enough that it's statistically significant or not? So if my samples from P and samples from Q are far apart, is this significant or have I been unlucky? Is it due to chance? And ideally what I would like is a large number of true positives. So if there is a difference, I really want to find it. So if I'm choosing a test or if I'm modifying my test, ideally I would want to make it as powerful as possible, as likely to find differences as possible when these differences exist. So then Witawat is going to talk about linear time interpretable features then for comparing distributions. So these are features that tell you not only that there's a difference, but where there's a difference. And he'll also talk about finding differences between samples and models where we know the equation for the model up to normalization. So just in terms of the scheduling, after each part we're going to take a short break for questions, and then there'll be like a little bit of a break at the end as well for further questions. But at the end of each part, you'll have the chance to ask a couple of questions about each of the bits. All right, so that's the outline. So let's talk about divergence measures. So I've got P and Q. Are they different? Are they the same? So there are 2 ways that one can think about differences in probabilities. I could take P minus Q. If P minus Q is 0, then P and Q are the same. Or I could take in some sense the ratio P to Q. And if this ratio, however I've defined it, is 1, then P and Q are the same. So these are 2 different ways that I might think about comparing probabilities, the difference or the ratio. So these two ways of thinking about comparing probabilities then give rise to a bunch of divergence measures. So the P minus Q approach gives rise to the integral probability metrics. So for these, I'm looking for a function from some smooth, some well-behaved class of functions that maximizes the difference in expectations under P and Q. But the fundamental tool here is a difference, P minus Q. Okay? If I'm thinking about the ratio, then this puts me in the category of phi divergences. So I have some function of that ratio. That function is going to return 0 when the ratio is 1. And then I'll take an expectation of that function that will tell me how far apart P and Q are. The phi function also needs to be convex, and we're going to see why later. Okay, so these are sort of my two categories of divergences, one based on differences, one based on ratios. So let's start with the integral probability metrics, and so within them we have the Wasserstein metrics, which you've encountered probably if you've done computer vision, and we've also got the maximum mean discrepancy. So we'll start with IPMs and then we'll move to phi divergences a little later. Okay, so to understand IPMs, I'm going to give an intuition. So let's say I've got these sets of points, red and blue, and I just ask you, like, are these from different distributions? And even knowing nothing about statistics, if you just glance at these points, you're probably going to say yes. Yes, they're from different distributions. Whereas if I give you these two sets of points, well, you're going to probably say, well, on the evidence of what you've shown me, I can't see a difference in the distributions. So these two sets of points seem to be closer together than these two sets of points. And an IPM gives a way to sort of formalize this intuition. So in IPM, I'm looking for a well-behaved function that maximizes the difference in expectation under P and Q. So well-behaved for this particular example means smooth. The well-behaved can be defined more broadly. And you can see that this function is very positive around my blue points, very negative around my red points. And so my EP of F minus EQ of F is large in this example. So now let's look at the second set of points. And here, because my function is well-behaved, because it's smooth, it can't go as far positive on my blue, it can't go as far negative on my red. And so the difference between my red and blue, according to this metric, is smaller than here. So I've captured this intuition that these points are further apart than these points. So this is an intuition. How do we define our well-behaved functions? So one way we can do it is to use reproducing Kernel-Hilbert spaces. These are spaces of smooth functions. If we use the unit ball in a reproducing Kernel-Hilbert space in an RKHS, then this is one candidate set of witness functions, okay? A set of witnesses that witness where P and Q are different. It's called the maximum mean discrepancy because I'm finding the function that pulls apart the mean as far as possible, so the mean under P and the mean under Q. So what are these functions if I'm using a reproducing Kernel-Hilbert space? These functions are weighted sums of features. So I've got weights, F1, F2, F3. I've got features, phi1, phi2, phi3. I take a weighted sum of these features, and that's my function. So there's the unit ball constraint. So the sum of the squared f's has to be less than or equal to 1. That's saying that my f is in the unit ball. And what you'll notice also about the features just graphically is that as I go down my list of features, they become less and less smooth, but their amplitude gets smaller and smaller. So I'm taking a weighted sum of features, but I'm deprioritizing the ones that are more wiggly. And so what I'm going to get out is a smooth function. Now, the power of reproducing Kernel-Hilbert spaces is that I can use infinitely many features. I can use an infinite dictionary of features, and I can compute those functions. But obviously, if I'm trying to implement this, then writing down infinitely many features can be a problem. So it so happens that if my algorithm only uses dot products, then if I use the right feature dictionary, I can compute these dot products in closed form, even though I might not be able to write down all of my infinitely many features. So, assuming that I can express my algorithm using dot products, then I can manipulate and take advantage of these infinite feature dictionaries. Okay, so let's give an example. Here is a feature map. Let's say it's infinitely long, but the sum of the squared features is finite, so that's what this little L2 notation denotes. And I'm assuming that I've chosen my features such that I have a closed form dot product K between the features of X and the features of X prime. Okay? So if I'm using dot products, I never have to manipulate these features explicitly. The features that you saw on the previous slide correspond to the feature dictionary of an exponentiated quadratic kernel. So you might know of this as a Gaussian kernel. Probably you shouldn't use it because it's too smooth, but this is the feature dictionary for that kernel. So if I'm using those kernels, if my algorithm is written in terms of dot products, then I can use these infinite feature dictionaries. Okay, so I've said that the maximum mean discrepancy uses a unit ball in a reproducing kernel Hilbert space. How rich does my feature dictionary need to be such that this is 0 only when P and Q agree? So it turns out the kernel from the previous slide is rich enough. These kernels are called characteristic kernels, and by characteristic I just mean I have infinitely many features, and therefore I can tell that P and Q are different when my MMD is not 0, and P and Q are the same when my MMD is 0. So, this feature dictionary is rich enough that I can always distinguish P and Q no matter what the difference is. So MMD is one integral probability metric, but there are many others, okay? So bounded continuous functions also induce an integral probability metric, which is interesting for textbooks. The functions of bounded variation 1 give you the Kolmogorov metric, so the largest difference between CDFs. And the functions that have Lifshitz norm bounded by 1 give us the Wasserstein distances. And we'll be using the Wasserstein distances a little bit more later. If you know of the energy distance, if you do statistics, that's a special case of the maximum mean discrepancy. Okay. So one very nice property of using functions in an RKHS is that I can take their expectations quite simply. So remember, I need to take the expectation under P of f minus expectation under Q of f. It turns out the expectation of f of x is a dot product of the coefficients f and the expected features of x, okay? So EP of f is dot product of f, the vector of coefficients, EP phi, expected features, and I'm going to denote as mu p this vector of expected features, and we'll be using that a lot. So one nice property that the MMD has, which is true specifically for the MMD but not for other IPMs, is you can also express it in terms of a difference of expected features. Okay, so let's see how this works. So this is our first proof, but it all fits on one slide, so stay with me. Okay, I've got my MMD. It's the smooth function that maximizes the difference in expectations. Remember what I said on the previous slide. The expectation of a function of x is a dot product of the vector of coefficients that define it and the expected features of x. Expected features under P. Okay, so mu p, expected features under P, dot product with f. So I've substituted that in, that's what's in the third line. So then I've got my dot product between my coefficients f and my differences of expected features under P and Q. Now look at the unit ball constraint. I need to solve that optimization problem subject to a unit ball constraint. So let's look at that graphically. Here I've drawn the vector of differences of expected features, mu p minus mu q, and now I've got my little f in a unit ball, and I need to maximize that dot product. So what is the f that maximizes that dot product? So it's not this one or this one, right? It's the vector, the unit vector that aligns with this difference in feature means. Okay, the unit vector in the direction mu p minus mu q. So if I use that, then indeed I get the norm of the difference of expected features under P and expected features under Q. So for MMD, the integral probability metric amounts to taking the norm of the difference of expected features under my P and my Q. And that's something specific to MMD. It's because I'm in a Hilbert space that I can do this. So I've defined my MMD in terms of infinitely many features. I've computed these witness functions, these smooth functions witnessing the difference of P and Q. But actually, how do I do that in practice? I don't want to deal with my infinitely many features. I need to express this using dot products so I can take advantage of the kernel trick. So here is my sample from P, here is my sample from Q. I'll tell you first how to compute the witness function, and then I'll tell you why the answer is right. So I'm going to use an exponentiated quadratic kernel, so I'm going to put these kernel bumps on each of my blue points and on each of my red points. I'm going to sum the blue bumps to get a blue function, the mean embedding of P, sum the red bumps to get a red function. I'll subtract red from blue, and that's my witness. So that was pretty easy. Why was that correct? Okay, remember that the f that solves my optimization problem is up to a constant of proportionality, the difference in the feature mean under P and the feature mean under Q. Let's say I've observed some points. So then I'm going to replace my feature means with my sample means. So here is my sample mean under P. What is my function, my witness function, computed at a point V? Well, it's the dot product of the coefficients that define it and the features of V. The coefficients that define it are the differences of the feature means under P and the feature means under Q. So I've got this sum of features of xi drawn from P, dot producted with features of V. I've got a dot product. I can use the kernel trick, and now I've got a sum of kernels centered at xi minus a sum of kernels centered at yi. So this explains how I got my witness function. So it's very easy to compute. And in particular, I don't need to deal with my infinite feature dictionaries. That's all implicit. That's taken care of. Okay, so that's the maximum mean discrepancy. Let's now look at an example in practice. So, I've got divergence measures. I've got a maximum mean discrepancy, I've got a Wasserstein distance, and so on. I need to understand when distributions are close and when distributions are far away under this divergence. So, if I were doing a testing problem, I would need to know if it's a difficult testing problem or an easy one. If my distributions are close, given the distance that I'm using, then it's a difficult testing problem. They're hard to tell apart. Okay, if they're far away, it's easy. Likewise, if I'm using a divergence measure as a loss, I'm training a GAN, I'm training an autoencoder, I need to understand, when my loss is small, in what sense are my distributions close? So it's important to understand how they behave. So here is one of the examples we'll look at. I've got P and Q, they've got disjoint support, and I'm moving Q towards P. I'm moving my red towards my blue. I want to understand how my divergences behave for this example. Okay, so let's first look at the Wasserstein 1 divergence. Okay, so how do I define the Wasserstein 1 divergence? This is an integral probability metric, but it's using a different function class to the one that I use for maximum mean discrepancy. So I'm using a function with a Lipschitz norm bounded by 1. Okay, I've defined the Lipschitz norm on this slide, but intuitively the way to think about this is to think of a function whose gradient is upper bounded by 1 all over the space. Okay, this is the Wasserstein 1, and as I move my red towards my blue, you can see empirically that it's decreasing. Okay, so I've used as a sort of visual cue to this like a nice teacher, a teacher that tells you as you improve your performance, you're getting closer. It's giving helpful and productive feedback. Okay, so if I'm using this as a loss, then this is a good thing. Now, I've been a little bit informal here, right? Because I've sort of said that as I move red towards blue, my Wasserstein is going down. I've given some references at the bottom of the slide where this is explained a little bit more formally, this notion that as I move mass from a starting point towards an ending point, my Wasserstein 1 distance is guaranteed to decrease. I also encourage you to read the optimal transport book that Marco Couturier and Gabriel Perret wrote. And there was also an optimal transport tutorial by Marco and by Justin Solomon at NeurIPS a couple of years ago. So I encourage you to watch the video of that if you're interested in understanding a bit more about Wasserstein distances. But for the moment, this is a nice intuition to have. As I move red towards blue, Wasserstein tends to drop. If I'm using that as a loss, to train a generative model, probably it's a useful loss. What about MMD? So here is MMD, and here I'm using quite a broad kernel. Okay, so MMD with a broad kernel is also, giving me helpful feedback. As I'm moving my red towards blue, then my MMD is indeed dropping. It goes, from 1.8 to 1.1. So for this choice of kernel, it seems to be a helpful divergence measure. It's giving me feedback that's telling me that I'm getting closer. But this is a factor of the choice of kernel that I used. So what if I use a narrow kernel? So I'm moving my red towards my blue, but the feedback I'm getting is sort of infinitesimally dropping, but not very much. That's not a useful gradient signal. So the visual cue you're going to get for this is like an angry teacher, that whatever you do, they just yell, no, it's wrong. Okay? And so MMD with a narrow kernel is like that. So is that a bad thing? Well, if I'm using it to train a generative model, then maybe yes, right? Because it's not giving me useful gradient feedback. What if I'm using it for testing? What if I'm using it to tell whether red and blue are different? Well, here it might not be a bad thing, because I'm very confident using this metric that red and blue are indeed different, okay, with a narrow kernel. So this is something that Dougal's going to return to in his part, like how to choose a good kernel when you're doing hypothesis testing. So we've spent some time on the left-hand side of the plot with integral probability metrics. Now let's spend a bit of time on the right-hand side of the plot and talk about phi divergences. So phi divergences, there's many divergences in this family. We've got the Hellinger, we've got the Kullback-Leibler, Pearson chi-squared, reverse KL, Jensen-Shannon, there's many, many divergences that live in this family. So let's define these divergences. Remember that for the phi divergences, the core ingredient is a ratio of p to q. Okay? So I'm going to take the expectation of a function phi of the ratio of p to q, and I'll take that expectation over q. That's the definition of the phi divergence. Now, we want it to be 0 when p and q agree, so phi should be 0 when it gets 1 fed to it. And we also need our phi to be a convex function for things to work out. Okay? It's also lower semi-continuous. If you know what that means, then you'll understand why it's useful. If not, then don't worry. An example that we're going to run with here is the reverse KL. So phi of x is minus log of x. And so this is going to give me the expectation of the log of q on p. So I've just flipped the order because I've used a negative log. And this is going to be my running example here. Okay, so let's go for our simple example again. Here is our distributions with disjoint support. The reverse KL is infinite. I've also put the Jensen-Shannon up there because the Jensen-Shannon is a popular phi divergence for GANs, and it's constant. Okay, it's log 2 as I'm moving my red point back and forth. So this seems at least to be a not very helpful teacher in the sense that if I'm using a phi divergence and I'm using it to train a generative model, if my support is disjoint, then it's not giving me useful feedback. It's not telling me that my mass is approaching its target. Okay? So on paper, this looks like it's my angry teacher that just yells no every time I do something. And yet, a million GAN papers tell me otherwise. So obviously, something's going on. And phi divergences seem to be, usable in practice. So let's figure out what's going on. Let's say that we're using a phi divergence in practice. I'm going to go with the reverse KL here. I need to express this in a way that I can compute so that I can then use it in a GAN. So the approach that we're going to take here is an approach given by the two papers that I've cited at the bottom of this slide. Nguyen, Wainwright, and Jordan published a paper in IEEE Information Theory in 2010, and then Sebastian Novotny and co-authors published a paper using that approach to train a GAN in 2016. So what I'm going to present is from these two papers. I encourage you to read them to find out more. So here is my KL. I want to compute it to use it in a GAN. I'm going to replace the KL with a lower bound, which is an optimization problem. Okay? I'm going to optimize over some f in some function class, which I'll define as I use it. It has to be negative in this case. And my lower bound takes the following form. I have the expectation under p of the function from this class, and I have the expectation under q of the log of minus f plus 1. So this log of minus f plus 1 comes from the dual of my phi that I use for my phi divergence. So if you haven't encountered duals before, duals are like a slope-intercept form of a function. So you give the dual a slope, it takes a tangent line at that slope, computes the negative intercept, and it returns that. So that's what a dual does. Okay? And you can prove, and that's what these papers do, that if you use this dual form, which in the case of reverse KL, the dual is minus log minus f minus 1, and then I've taken a minus sign in front of all of that, so I get plus log minus f plus 1, then I get a lower bound on my KL. And the lower bound becomes tighter as I optimize over my function class h. So if I optimize well, my lower bound's going to be tight. So how can I get a tight lower bound, like the tightest lower bound? Well, the tightest lower bound comes when I use f diamond here, which is a negative ratio of q to p. Okay, so now you know where the f has to be less than 0 comes from, because I'm getting a negative ratio of densities, which has to be negative. Okay? So here I've plotted an example. So I've got a Gaussian distribution for both my p and my q, and I've plotted here the ratio of q to p. I've plotted it on a log scale because otherwise it's going to blow up, right? And you can see that that's revealing where it's positive when q has more mass, it's negative when p has more mass. But it should worry you a little bit that it's blowing up as much as it is, because if I'm using like a well-behaved function class in h, then that doesn't like functions that dash off to infinity with slope that's increasing. So this might be a little bit of a problem if I'm using a well-behaved function class to compute my KL. So hold that thought because it's going to come back. So now let's say I've got a lower bound, I've got samples from P and Q, I don't have the population P and Q, I want to approximate this lower bound with samples. So that's what I'm going to do here. I'm replacing my population expectations with sample expectations. So expectation f of x, expectation minus f of y plus 1. Okay? So what we've got here is a KL approximate lower bound estimator, which we're going to call the KL divergence. So a lot of people have used KL divergences in GAN training, but in fact they've used KL divergences, which sounds like the same thing, but it's not. So let's see how the KL divergence behaves in our example. Okay, so here is our KL divergence for the negative KL. We're going to use a particular smooth function class, which is the exponential of an RKHS function here. So e to the inner product of w and features of x. Okay, we're going to penalize the norm of w, which amounts to a smoothness constraint. So this is actually a very smooth approximation of the ratio of the densities, which we're going to call the KL smoothie. So let's see how the KL smoothie performs. And in fact, this is a helpful teacher, right? Because the KL smoothie is in fact dropping nicely as my red points approach my blue points. So the KL, the actual divergence we're trying to approximate, that's going to be infinite. And it's not going to give a helpful feedback. But this KL divergence, the KL smoothie, actually is helpful. So it is giving me helpful feedback as my red is approaching my blue. So using a smooth estimate of this ratio, like that's got to be a good thing, right? So here it is. But you can find examples where it's not. So here's an example where it's not. So this is the example of mode collapse. So on the x-axis here, I've got two Gaussians. The red one is getting thinner and thinner as I move along my x-axis. So the red one, the mode of the red one is collapsing. Now, as the red one gets thinner and thinner, the ratio is going to explode, right? The ratio of Q to P is going to blow up. But I've insisted that I want my ratio to be a smooth function. I'm using a KL smoothie. That's a smooth function class for my ratio. So what you'll notice is that as the KL goes up, the KL, the KL smoothie, plateaus because I've introduced a bias by forcing my ratio not to be too rough, okay, not to be too spiky. So in this case, using this smoothed approximation to the KL has got me into trouble because it's meant that I haven't noticed mode collapse as much as I should have done. Okay, so sometimes it helps, sometimes it hinders. So I'm going to end this part with a nice example of a paper which is using divergence measures in practice in an algorithm for training a generative model. So this is the Wasserstein autoencoder. It's a really nice paper. I encourage you to read it. It's by the team at Google Zurich. And just to give you a simple idea of what it's doing from this figure, the encoder is taking images in my X space, which is at the bottom of my slide, and it's encoding them into the space of latent variable Z, which is at the top of my slide. So each image gets a different code word, and these are these blue arrows that appear on the slide. Okay? Now, the Wasserstein autoencoder is going to match the distribution, the marginal distribution, over these encoded variables with a reference distribution P. That reference distribution in their paper is Gaussian. Okay, I'm matching encoded variables in some code word space with a Gaussian. And I can use a divergence measure to do that. So I could use either an integral probability metric, an IPM, or I could use a phi divergence, okay, which I would need to approximate. So I'll approximate, or they approximated it in this paper using a neural network class. So these are the neural network divergences that Aurora and co-authors talk about in their paper. Okay, they're using not the reverse KL, they're using the Jensen-Shannon, but it's a phi divergence, same strengths and weaknesses apply. So let's look at some results. So here is the performance in FID score on Celebi for the Wasserstein autoencoder. They're using two different divergence measures, the maximum mean discrepancy, so that's the IPM they're using to match the encoded variables with the Gaussian, or they're using a GAN, which is using Jensen-Shannon. Okay? And what you'll see here is that the FID scores are pretty much the same, like one's a little lower than the other. Both are quite a bit better than the variational autoencoder. I should emphasize, by the way, that these are the results for the latest version of the paper on arXiv, which are better than the original published version. And the reason why is because they did like a really comprehensive parameter sweep. So is this the whole story? So if this was all that you saw, it would seem that both methods are like, interchangeable. But it's interesting to see how these methods behave as one does a sweep over all of the parameters, over the, the critic network, over the encoder architecture, over learning rates, etc., etc. So here we are showing two box plots for each method for different bottleneck dimensions. So on the x-axis, I have either 32 or 64. So this is the dimension of my code word that I'm showing on the x-axis. And then these box plots are box plots over everything else that I might want to do to adjust my algorithm. So they've done like a sweep over pretty much everything you can think of. And what you'll notice from these plots is that if you're using an IPM, the result is a lot more stable than the result that you get when you're using a GAN type approach. And the reason for this is that, a phi divergence fundamentally relies on a ratio. Okay, that is the core ingredient for all phi divergences. Now, if my encoder happens to have put mass in such a way that it gets concentrated, then, my ratio wants to blow up. So it really matters that I regularize that ratio, that I smooth it in the right way. Otherwise, I'm in trouble. So basically, if I don't do it the right way, then my algorithm becomes unreliable. If I do, then I'm good. So smoothing really matters in this case. Whereas for MMD, it's based on a difference in measures rather than a ratio of measures. So it's a bit more stable when I'm doing my parameter sweep. Okay, so that's was the Stein autoencoder. So let's go back to our original figure. On the left, we have our integral probability metrics. On the right, we have our phi divergences. So one depends on a difference of measures, one depends on a ratio of measures. But my circles are overlapping a little bit. Was this like PowerPoint mishap or not? Okay. So it turns out that there is something that lives there, and that's the total variation distance. Okay. That is the only measure of difference between probabilities that is both an integral probability metric and a phi divergence. It's the only non-trivial one that lives there. So it's the L1 distance between P and Q. There are no other non-trivial measures that live at the intersection. Okay, so that concludes the first part. I've got some references here. The slides will be online, so you can grab these later. So we'll take a short break now for questions and to switch slides. Any questions? Oh, there are microphones. Where are they?
Along the aisles.
Along the aisles. So since, I'm old and my hearing is poor, best to use the microphones.
I think they're there somewhere. Oh, back there. Oh, yeah. Okay, there's a question over there.
Okay, yeah?
So I remember reading a paper a while ago which looked at relativistic F divergences, which proposed to fix like some of the issues you see in GANs using F divergences by like penalizing like the probability mass assigned to the observed, so like original data, as your generator gets better. So kind of mixing the IPM and the like F divergence approach. You said TV is the only non-trivial like intersection. So do you know this paper, can comment on that, or?
Yeah, so thank you for telling me about the paper. So if I didn't quite understand your explanation of what it was doing.
I can try to do it a bit better from memory. Basically, the argument that I was making is that as the generator gets better in a GAN, the discriminator assigns more and more probability mass to the fake data, but it doesn't think of the observed data as less likely when it sees them. So it doesn't forget about the true data. Versus with Wasserstein GAN, it actually gets harder and harder to tell the two measures apart. Was kind of the argument they were making. Okay,
so no, I mean, I think the idea of reweighting your samples as you train, like that's probably going to help with GAN training. What I don't know if it will help with is the issue of measures with disjoint support if I'm using an F divergence, because by the definition of the loss you're using, if the support is disjoint, the ratio is going to be infinite. But I'm interested in the paper. I didn't know of it, so I'll take a look. So thank you. Yeah.
It's not my paper, just to make it clear.
Sure. Yeah. Okay, yep. Is there another mic? Because I want to make sure that I give everyone an equal chance. So, yes?
So in traditional hypothesis testing, you would generally look at the likelihood ratio, and that would be the right thing to do. So somehow, how does that fit into your story?
Sure. No, so that's a very good point. So if we are doing hypothesis testing and we have two parametric alternatives, then the likelihood ratio is the uniformly most powerful test. And that's the rule. Now, if we have basically, P and Q, which are not from two alternative parametric families, but we've just got samples, we don't know anything about those distributions, at that point, you cannot define the likelihood ratio because you don't know the likelihoods. So then we're interested in the tests that we might use in the circumstance where we've got samples, but we don't have a closed form expression for the likelihood. Yep. Yes?
So first of all, thank you very much for this great overview of the divergence measures. My question is related to what you mentioned during the talk, is that GANs use Jensen-Shannon divergence, is what you said?
Yep.
So if I remember correctly, that was just the analysis that if you reach a Nash equilibrium, you have minimized the Jensen-Shannon. But I'm not aware that GANs actively or explicitly use Jensen-Shannon. Can you comment on this?
Right. So I think, the goal of the GAN, I guess the goal of the GAN loss is to hit Jensen-Shannon, but it's doing this using this variational form. So I'm going to even give you the shape of that variational form for the Jensen-Shannon. It's right here. It's messy, which is why I didn't use that. I used reverse KL instead. The function that optimizes that is also a ratio function. It's 2p on p plus q. Now, what happens when p is 0? When q has support, I've got log 0, so I'm in trouble. So, if I have disjoint support, I can still run into problems with a Jensen-Shannon. So the same sort of issue applies, but I can use smoothing, right, as I did for the KL. And if I do that, then I get a helpful divergence. And, this seems to be what's helpful in practice as well.
Okay. Thank you very much.
Is there one over this side before I go to this side again? No? Oh, yes.
Pardon, I have a question.
I cannot see, there's too much light. Okay. Great. Yep.
Is there any, by the way, compliments, very, very interesting talks.
Oh, thank you.
Is there any relationship between the KL divergence and elbow?
An elbow is a lower bound on a KL, but in a sense, when I'm using KL in the sense of leafy vegetable and approximation to KL, one of the, core components is this function class. So I guess I would be interested to, to explore this a little bit more, but I don't have an answer off the top of my head for that question. Yeah.
Thank you.
Yep.
Can you comment on when is a curse of dimensionality a problem and when it's not? Because, for example, in the one of your slides, you use the kernel, and that's going to blow up, and it's not useful in high dimensions, right?
Mm-hmm. Yeah. So when is curse of dimensionality a problem? The answer is always. In the case of the variational autoencoder, we're in 64 dimensions, or, the most dimensions you get is 256. So here it's not a problem because the dimension is low. Now let's say that I'm using an integral probability metric to train. Again, then I'm talking about image space. That's very high dimensional. So in this case, if I was using an IPM, I would probably learn some features to basically simplify my problem. If I'm learning features, I need to use a gradient regularizer, or a spectral regularizer, or both. And so then, the way that we sort of simplify the problem is by smoothing the class of critic functions that we use to define, our IPM or our KL estimate.
So what if you want to compare the distribution directly in the input space, as you did at the beginning of your slides? So then you cannot use the kernel, right?
So Dougal is going to give you a lot more detail on that than I will. Yep. Shall we continue? Yes. Okay, so we're going to just switch slides now.
Okay.
Yeah, this is just for the recording.
Hopefully that's all good. Okay, so now that Arthur has told you lots about ways to measure different notions of distances between probability distributions, I'm now going to talk about how you actually use those distances to solve some problems. So the section I'm going to talk about is two-sample testing that Arthur mentioned at the start. So an example of this problem, actually relating to the very last question we had, is shown here. This is, if you've seen this, so probably most of you are familiar with the CFAR10 image distribution, very common distribution used to, for computer vision tasks. And you may have seen this CFAR 10.1 thing, which was an attempt by some people at Berkeley to make a new test set for CFAR 10. The reason they did that was for, reasons related to trying to understand overfitting, stuff like that. But if you read that paper, they ran into some weird conclusions. And part of their explanation was, well, what we saw might make sense if these two distributions of images are different. But if you just look at them, it's hard to tell if they're different. So that's the kind of question that we want to answer. Given two complicated distributions, or two samples from complicated distributions, are the distributions that these images we actually see are sampled from the same or not? And so, as Arthur just told us, for a lot of choices of kernel, for example, the MMD will be 0 if and only if the two distributions are the same. So what we do is we just evaluate the MMD between the two distributions, and if it's 0, we're done, right? So the first question is, how do you actually estimate the MMD? So Arthur showed a couple forms for the MMD, but not quite one that's easy to implement on a computer. So I'll show you how to actually do that now. So remember, this is one of the forms that Arthur showed us, the distance between the mean embeddings, these like average features of the two distributions. So what I'm going to do is I'm just going to do a normal linear algebra thing, write a squared norm as a bunch of inner products. And now if you remember the definitions of what these objects are, these mean embeddings, they're the expected features of sample sets, right? So if I do that, and then I just pull an expectation out, I get this form. And then the definition of a kernel is that the inner product between these features is some function we can actually evaluate. So now this form for the MMD is the average of the kernel value between, within the distributions and across the two distributions. So what does that look like? So let's go back to the dogs and fish and show you how to compute that here. So here we have a bunch of images of dogs, we have a bunch of images of fish, and what I'm showing here on the right is a kernel matrix where each entry of this is the kernel value between one of the dogs and one of the fish, or two dogs, or whatever. And the expression I just showed you, this is the form of the squared MMD. It's the expected dog to dog plus fish to fish minus dog to fish. So I can just take that expectation, take an empirical average, and then I have a pretty obvious estimator for the MMD. Now this is something that you can easily compute. You just make this kernel matrix, and then you take averages of the different blocks. That gets you out a number, right? Okay, so I can do this on my images. I'm not going to tell you what kernel to use or whatever right now. I'll tell you that later. But say we do that, and we get some value as an estimate for the MMD. This is a totally made up number. I didn't actually run it here, but pretend I did, and I got 0.09 out. Well, 0.09 is not a big number, but it's also not 0, right? So is the true MMD 0 or not? I don't really know, right? So what I have to do is try to understand, based on this estimate that I have, what's the true value. So we need to know, in some sense, how the randomness in this estimator works. So here's an example of how the randomness in the estimator works in a simple case. Here I'm comparing two distributions, these blue and the red points shown in this picture here. And what I'm doing here is I'm drawing 200 samples in these 2D points. They have different variances in the y direction, but the same in the x direction, whatever, details don't matter. Now when I run this MMD estimator, I get, say, 1.2. There. Here's a histogram of 1 point. It's 1.2. Now, because we want to understand the randomness, let's just do this a lot of times and see what happens. So now I'm going to draw a fresh set of samples from the same distributions, compute the MMD again, and this time I get 1.5. If I keep doing that more and more times, my histogram will converge to something that looks like this. And if you squint at that a little bit, it looks pretty much like a normal distribution, right? And normal distributions are nice, so maybe the asymptotics of the MMD are a normal distribution. Turns out that's true. So what I've written here on the top of the slide is something that if you remember how like central limit theorem results are usually written, that's what this is. Basically what this says is the MMD estimator is asymptotically normal with a mean at the value of the true MMD and a variance that is this sigma squared over n. So sigma squared is a constant that doesn't depend on n. It does depend on p and q and what kernel you choose. But the variance decays asymptotically like 1 over n. So that's the shape of what it does in this case when the two distributions are different. But when the two distributions are the same, actually the asymptotics are a little different. So let's check. Here's a case where both of my distributions are just standard normal. So I'm doing doing the same thing. Here's 10 MMDs. This isn't looking so normal. And it turns out that actually this is not a normal distribution. This ends up being an infinite mixture of chi-squared distributions. And this is a little more complicated. We know it is a particular distribution. And if we want, we can try to estimate it. But the problem with this is unlike things like a t-test or something like that that you probably saw in Stats 101, this distribution actually depends on your choice of kernel and what the distribution of the data is. So it's not something you can like write a table for in advance. But it is, we do know that it converges in distribution to something, and that's really helpful. Also note, before I was multiplying the MMD by root n because the variance decayed like 1 over n. Here I'm multiplying the MMD by n. The variance actually decays a lot faster in this case. So this is just summarizing what I just showed you. We have two cases for the asymptotics, right? In the case where the distributions are different, we have a normal. In the case where they're the same, we have this mixture of chi-squared. Now what do we do with this information that we just did a bunch of math to find out? Well, what we want to do for a reasonable thing to do is to do a kind of classical statistical hypothesis test. And so the idea there is we have a null hypothesis, which is that the distributions are the same. And if my estimate of their distance is pretty big, then I can be confident that the distributions probably aren't actually the same. It's very unlikely that I would have seen such a high difference by chance. If my estimate is less than whatever threshold pretty big means, then maybe the distributions are the same, or maybe they're different, but I just didn't have enough data or I wasn't looking in the right way to tell that they're different. Okay, so what we're going to do is we're going to take the MMD estimator, multiply it by n, because then we know we get a consistent threshold. And then we're going to ask whether our estimate is bigger than that threshold C alpha. So the question is, how do we choose C alpha? Well, the traditional statistical way is we want to say, under the null hypothesis, so when p equals q, we want to make a mistake. We want to reject the null when it's actually true with a rate at most, say, 0.05 or something. I'm going to call that alpha. And so we want the probability of doing that to be less than alpha. And the probability on this plot is just this area, this green area here. It's the probability that our estimator is bigger than the threshold in that case. So we need to find that threshold, set it that way. And then how good our test is called the power. That's the probability that when the two distributions are actually different, that I correctly identify that they're different. So we want the setup of traditional statistical hypothesis testing is we want to choose alpha and then get the highest power we can for that choice of alpha. Oops, too far. Sorry. So let's go back to dogs and fish. And this is just a reminder of what we're doing. So we take our dogs and fish, we build a kernel matrix, and then we estimate the MMD. Now the question is, how do we find this C alpha, right? This asymptotic distribution, we know it exists, but it's a little complicated to figure out exactly where that threshold would be. Well, the observation that we're going to make is that in the case where p equals q, under the null hypothesis, the dogs and the fish are actually the same thing, right? So if I mix them together, I didn't change anything. So what we're going to do is we're going to mix the dogs and fish together, right? Dogs and fish sometimes are the same. And then we're going to look at what my estimator does once I've mixed them together. So the way I do that is I take my samples, I shuffle them all together. So now I have a new X tilde, which is a random mixture of dogs and fish, and I have a new Y tilde, which is the other half of the random dogs and fish. And what that corresponds to in terms of the kernel matrix is I'm going to, it's the same entries, but I'm going to shuffle the labeling around. I'm going to move the rows and columns. And then I'm going to do the same thing. I'm going to estimate the distance between X tilde and Y tilde with this new shuffled thing. And that'll give me an estimate of what happens in the case when P actually equals Q, right? So if I do that a bunch of times, if I do that 1,000 times, and then I say, okay, what is that distribution? Like, what is the 1 minus alpha quantile of that distribution? That'll be a pretty good estimator of what the actual threshold should be under the null distribution. Okay, so that's called permutation testing. And now, given a kernel, we have all of the ingredients that we need to run a test, right? So the only thing we have left to do, we're given the data just by what problem we want to solve. We know how to run a test. Now we have to pick a kernel. So as Arthur showed us before, if we choose some simple kernels, like here this exponentiated quadratic, also goes by other names, it is true that no matter which bandwidth we pick in this exponentiated quadratic, the kernel is called characteristic. And what that means is the test is consistent. No matter what bandwidth I pick for a fixed pair of distributions, as I see infinitely many samples, my power will eventually go to 1. That's just because the null distribution scales like root n and the alternative scales like n, so eventually, all of that mass is going to escape to the right in that plot I showed earlier. The problem with this is that we never have infinitely many samples, right? And we actually have a finite number of samples. This choice of bandwidth matters a lot. So here's an example of a really easy testing problem, blue versus red in these points here, right? And if I choose a reasonable bandwidth, I get a witness function that looks like this. You can imagine that this witness function will give you it's a nice smooth class of functions that will give me a high MMD. And so I'm going to be able to confidently say these things are different. But if I choose too big of a sigma, so I choose too smooth of a kernel, then I get a witness function that looks like this. And this witness function can barely distinguish between the two distributions, so my MMD value is going to be really small. And so I won't have as good of a power with this class of functions until I get so many samples that I can actually tell the difference between the slightly higher and the slightly lower parts of this function. If I choose too small of a sigma, then I get this really awful bumpy thing. And this actually gives you a really big value of MMD, right? The function is really high on all the blue points and really low on all the red points. But when I do the permutation thing, that's still going to be true. Even when I've shuffled all the blue and red points together, I'm still going to have a really high MMD, and so my power is going to be really low because my rejection threshold is going to be really high. So this low value of the kernel bandwidth is also bad. Also, if we're doing more complicated things, like high-dimensional problems like images, as we were asked about earlier, it doesn't matter what bandwidth you pick. No choice of bandwidth is going to be a good choice for complicated image problems, right? Because this bandwidth is based on the kind of pixel distance between images, and pixel distance between images is just a bad notion of distance between images. Okay, so what are we going to do? As Arthur hinted at earlier, one thing we can do is we can just use some representation of the images other than just the raw pixel values. So here I'm showing this as some function phi that's mapping our original space, say images, into some hopefully lower dimensional, more meaningful space. And if I know a representation phi like that, then I can actually define a kernel on the original points by using some kind of intermediate kernel, this k-top thing, on these representations. So here's a couple examples of this kind of fixed a priori, and then in the second half of this section, I'll tell you about how to actually learn a phi. But if you do have some kind of meaningful phi, is useful for this kind of data, then maybe you can just use that. So for example, if you're doing images, maybe you could do something like take a pre-trained ImageNet classifier and look at the class labels that it spits out on your data, right? And so if the distributions are the same, they should spit out the same class labels, and this may be a useful way to measure the distance. This is related to some of the earlier notions of GAN evaluation that people used to use. And if your classifier is actually relevant to your data, that can be pretty good. We're going to come back to this notion later. Something that works a little more reliably than that is to not actually take the class labels from your related thing, but take some hidden layer near the end of your classifier. This is generally something that will generalize a little better between domains and tasks. And so you can measure the MMD between images based on, say, 2,000 dimensional hidden representations that you get from an ImageNet classifier. So one notion of that is something we came up with called KID. There's a very related notion in this paper by Xu et al. That was simultaneous. And this is very closely related to the FID score that Arthur mentioned earlier, which I'm not going to go into, but it's essentially this, but you estimate Wasserstein instead of estimating the MMD. It turns out that both using MMD gets you way nicer statistical properties, which look at our paper's appendix for a bunch of that. And also there's a paper in this conference called HYPE, where they put a lot of effort into really doing the best possible human evaluations of GAN models. And they found that their score correlated much better with with KID than it does with FID. So, it's a nice notion of distance. Here's another one that is from a paper that just came out at ICCV. What they do here is they're looking at GANs, and they're trying to understand what kind of images GANs are generating on this Elson Churches data set. So there's a lot of images of, tourist type images of churches. So what they do is they run these images through like image segmentation model that classifies each pixel in the image as building, sky, person, etc. And then what they do is they represent the image as the count of how many pixels are in each of the classes that they use. And then they look at the mean of that over the whole data sets. You can think of that actually as the MMD with a kernel that represents each image by this vector of pixel counts in each class. And then the kernel is you take dot products of those pixel class counts. And now what they're plotting here is just the mean embedding on that kernel that does a linear kernel in the counts. And you can look at this mean embedding and you get really informative notions here. Like you can see that most of the pixel counts more or less match, but some of them are way off. Like it doesn't produce nearly enough palm trees apparently, and it produces way too many rocks. That's not, something you would necessarily notice just looking at a few images, but you can see it when you look at everything like this. The other thing that so in this paper, they did this and they showed a plot like this and they tried to get some quantitative notion of how different the two distributions are based on this. Because the question is, how much of this might be due to chance. But if you use this MMD framework with this as a kernel, you can actually get a statistical test out of it doing exactly what they did. Okay, so Arthur spent the first bit of the talk talking about all kinds of other distances, and you might ask, well, can I run tests with those? Of course you can. One issue is that for a lot of these distance estimators, the asymptotics aren't so well understood. There's some special cases where we know things about them, but for the most part, things like the Kale or most Wasserstein estimators, it's just really hard to analyze. But it doesn't necessarily matter because you can always do permutation tests and you can always run a test like that. So that's a thing to keep in mind. Okay, so we've talked a little bit about how you might pick, by hand pick a kernel that's good for your particular problem. But how can we be a little more general than that, right? This is a machine learning conference. How can we learn? So reminder that the power depends on the distributions. And you can choose lots of things that will eventually work for any pair of distributions. But you're not going to be able to pick a kernel that always works for any problem, right? That would be what we would ideally like, but it's kind of a ridiculous thing to ask if you think about it. It's kind of like saying, what classifier can I use that will always work for any problem? There isn't one, right? You have to adapt to the data some. So how can we adapt our kernels to the data in that way? So remember, we want the kernels with the highest power. And so, well, let's look at the power and see if we can, do a little math to understand what's going on with the power there. So here's the expression for the power, right? The probability that our test statistic is bigger than the threshold that we estimate. Here, C alpha hat is our estimate of the test threshold, and this PR1 means probability under the H1, that the two distributions are different. So if I can take this, and I can rewrite it like this. It's not immediately obvious, maybe, but I didn't actually change this event here. I just, divided both sides by root n, subtracted, and whatever. If you stare at it for 2 minutes, you can see that they're the same thing. Now, this thing on the left here, though, is exactly the thing that I said converges to a standard normal. So as we see more and more data, this probability is going to converge to this kind of Gaussian probability here, where phi here is the CDF of the standard normal. So look at this expression, and we can see the power for large n is going to look like this, right? But now also for large n, the first term, MMD and sigma are both constants, and so is c. So the first term grows with root n, and the second term shrinks with root n. So if n is reasonably large, this second term is going to be tiny, right, eventually. So we can usually just ignore it. And so this first thing, the only thing that we have to maximize then is this ratio of the squared MMD to the standard deviation of the squared MMD estimator. Now, if we look at this for a minute, you might think, oh, to have a good test, I should just find an MMD, I find a kernel so the MMD is large. And that's true. You absolutely want a large MMD between your distributions. But the thing is, you also don't want the case where your MMD is large, but the variance of your estimator is also huge, right? Because then when you get any particular estimate value out, you're not going to really know whether it was big because of the true value is big or big because the variance is big. So it turns out the right way to trade off between having the estimate be big and being confident in your estimate so you can be sure it's bigger than your test threshold is to divide this way. And also, I'm not going to, so we showed how to estimate the numerator here, MMD squared. There's also a simple way to estimate the denominator, the sigma, but it's kind of gross to put on a slide. But it's something you can write down in PyTorch or whatever, and it's differentiable, and you can just maximize it in terms of your kernel parameterization. So I'll talk about how to do that in a second. So if we're doing this, it's important that we don't trick ourselves, right? That we keep everything statistically valid. Because if we optimize on some data and then we evaluate on that data again, we're looking at the training error, right? And we need to look at test error. So what we do, given some data, is you can split it. And you can use part of your data to learn a kernel, maximizing the estimator of that thing I just showed you. And then once you've learned a kernel, you actually run a test using that kernel on the other half of the data. So now this second part is exactly the standard testing framework that I talked about for the first 15 minutes of this section, right? So we know how to do that. And we also know how to do the first part. That's just writing down a loss function in PyTorch and hitting optimize, right? So we know how to do this. So what does that do? So learning a kernel is actually really super helpful. Here's a toy problem to illustrate it. So here I'm showing two distributions. This up here is a sample from the distribution P. It's one distribution that lies on this grid, right? And here is a sample from the distribution Q. It's another distribution that lies on the same grid, but the blobs at each grid point are different. So epsilon here is it's the ratio of the eigenvalues. It's how slanted each blob is. So when epsilon is 1, they're actually the same. When epsilon gets really big, they become basically diagonal lines on the grid. So the problem gets easier as epsilon is bigger. So here I'm showing what happens in terms of the power, which is so here they're actually the same. Everywhere else the distributions are actually different. And I'm showing as you just choose the bandwidth of an exponentially quadratic kernel. If you use the kind of heuristic that people usually use, you set to the median bandwidth, you don't learn anything, you just use a rule of thumb, then on this particular problem, it doesn't work at all. It works usually on a lot of problems, but it doesn't work on this one because it was designed specifically to not work for that. But if you optimize, you can get something that's actually nearly the optimal choice among all possible exponentiated quadratic kernels. You can also do a lot more than just learning a bandwidth, right? So here, I'm doing a deep kernel. And what I mean by this is I'm taking that representation phi that we were using before, but instead of having that be something fixed that I just picked up somewhere else, I'm going to parameterize some deep network layers and then learn the parameters of that deep network to get the best kernel. And so here you can see on a different version of this blobs data set where the different sections have kind of different directions of correlation. You can see that the kernel has learned the different directions in different parts of the space. You can also do it back to this problem I mentioned at the start of comparing CFAR10 to CFAR10.1. And it's a little harder to plot, but we can actually, using this method and making this phi a convnet, you can actually pretty confidently say that the marginal distribution of images is different between CFAR10 and CFAR10.1. Okay, so since we're at a machine learning conference, probably at some point during this so far, you've been thinking, well, why don't I just train a classifier, right? I'm distinguishing two things. Classifiers, we know tons about classifiers. So actually, that's a pretty reasonable thing to do. It's proposed, for example, by this iClear paper, but lots of people have done this over the years. Basically, what you do is you split the data again. You train a classifier on half of it to distinguish X from Y. And then you evaluate how accurate that classifier is on the other half of the data. So if your accuracy is 1/2, then you can't say that they're different. If your accuracy is 100%, obviously the data distributions are different because you can totally tell them apart. But even if your accuracy is 60%, like, is maybe not the best classifier ever, but the fact that you can classify at all tells you the distributions must be different. It turns out, the reason I didn't start with that is this is actually a special case of the MMD approach. So if you imagine taking this kernel that we've learned, this classifier that we've learned, F, and then constructing a kernel like this. So this is a kernel that evaluates, like, given X and Y, it says, did I classify X as positive? Did I classify Y as positive? If I classified them both as positive, the kernel value is 1. If I classified either one as negative, then the kernel value is 0. If I take this and I just plug it into the definition of MMD and do a little algebra, you get out that the MMD is actually the accuracy of that classifier minus 1/2, like, absolute value. So it's almost exactly the same thing as this classifier test that I just said. Of course, here we would want to, parameterize F and maximize F. So if we do that in this framework, we take this kernel and we maximize the MMD over its standard deviation. It turns out that the standard deviation also decreases as the accuracy gets bigger than 1/2. So it's actually almost exactly the same. If we do it in this framework, we're just finding an F with highest accuracy. The problem with doing it this way, of course, is that this 0-1 kernel is, you can't differentiate it. It's not easy to optimize that way. It also, by taking the 0-1 kernel, actually the variance is higher. Because you can think about it as like the variance of a Bernoulli is much higher than the variance of something else that's bounded in 0-1. So your test power is actually lower by using this 0-1 kernel. You can do something kind of an intermediate option where you just take the the probability outputs of the classifier, and that'll empirically, at least on some problems we tried, we saw that using the 0-1 kernel tends to be somewhat worse than using the probability outputs, which would compare the mean probability between the two classes. And that tends to be somewhat worse than doing this deep kernel with some kind of hidden representation. The other difference between this classifier case and our approach is that in the classifier case, of course, you can't train directly for accuracy. That's NP hard, right? But instead, you train for this cross-entropy thing. That's something that's actually differentiable, and we know how to do that, even though that's also NP hard. But it's something that you can actually reasonably do. So it also turns out, at least on some problems that we tried, that our criterion here of the MMD over its variance tends to work somewhat better than training for the cross-entropy in cases where you can do both. Okay, so I'm going to end now with a few words on interpretability. So here's the problem that Arthur mentioned earlier of this GAN criticism, again on MNIST. And the question is we want to distinguish these two distributions, and it turns out the answer to this is they're different. And even with a trivial kernel, you can actually tell that they're different. One of the ways you can tell, for example, is that the GAN doesn't output digits exactly like in the 255 possible pixel values, right? It does continuous things in between. That's a really stupid difference that we don't care about, but that's a difference you can find immediately. So we want to do something where we can kind of understand the difference, and if we see something stupid like that, we can correct for it and try to understand a little better what the difference is. So here's something we can do. We can take what's called an ARD kernel, automatic relevance determination. So what we're doing is we're taking this image, we're breaking it up into its pixels. In this case, it's only 784 pixels. And we're going to learn a separate bandwidth for each individual pixel of an image. And then our kernel between two images is going to be the product of this like exponentiated quadratic kernel between each pixel of the image with a different bandwidth for each pixel. So if these were all the same, it would be a normal exponentiated quadratic, but we're learning different ones. So if I do that in this case, first of all, by doing that, I can get a much higher power for this ARD kernel than I do for the RBF kernel. At a RBF meaning exponentiated quadratic. So for a particular sample size, you can get like 100% power for the ARD, where you're only getting like 50-50 power for the regular exponentiated quadratic kernel. You can also look at what the ARD weights you learned are. And so you can see that by looking at these pixels, so mostly this kind of diagonal thing down the middle and mostly ignoring these parts, you can find a good difference. So that tells you something that like maybe the ways that the GAN is wrong, you can see that the GAN is wrong by looking at these points. You can also do something a little different, which is looking at the points that the witness function cares about the most. So we can take a bunch of samples from the data set, we can take a bunch of samples from the GAN, and we can just plot what is the value of the witness function on them. And so here, in this image, the histogram of the witness function values mostly overlaps a lot. This tells you that the MMD value is not very high because the means are very close to each other. But certain points, so first of all, the MMD value is very small, but it turns out the variance is really, really, really small, so you can get a really confident test. Also, the points that have the witness function like that it thinks is most like the data set are these images. And so you might look at this and say, okay, well, it seems like maybe the GAN is underproducing these vertical ones, and it's overproducing images that look like this. Here's a related example from an earlier paper, going back to dogs and costumes, where what they did in this paper is they basically took ImageNet and they said, okay, we have a method where we want to summarize a bunch of images by some prototypes. So they took this particular class from ImageNet of this kind of dog, and they say, here are our prototype images. They have a particular method for doing that. It's actually based on the MMD, but so they minimize the MMD between their prototype images and the overall thing. Great. But then they say, okay, well, we've learned this model, but what can we say about this model? Where is this model wrong? It turns out, by looking at the points where the witness function most identifies things as being more indicative of the true data set and not their model, you get these images. So images like dogs wearing costumes, or where there are a bunch of dogs standing around rather than a close-up picture of one dog. So things that their prototype has missed, and it helps you understand the difference between the distribution of overall ImageNet and their distribution of prototypes. Okay, so when Widwat takes over in 5 minutes, he's going to talk a bunch more about interpretability and also move on to the model section. But in the meantime, here are kind of the main papers that I talked about in this section. Again, the slides will be online in a minute, and we have another few minutes for questions if there are any at this point. Or if you want to run to the bathroom or whatever.
Thanks for the great talk. I was just curious, most of the examples that you're giving are related image processing. For natural language understanding types of tasks, any specific kinds of things to pay attention to that might be a little bit different?
Yeah, so I've mostly worked with image data, is why I'm mostly focusing on the image stuff. People have worked in this kind of setting on natural language. One issue is well, I don't know so much about NLP, so I'm not gonna try to say too much. But there's the normal things where when you're dealing with discrete data, it's hard to do differentiable stuff to maximize the criterion and stuff, and you can use any of the normal things people do in natural language processing for that purpose. But I'm aware of a bunch of work doing MMD stuff with natural language, a lot of times based on word vectors and like distinguishing document distributions and stuff like that. I haven't seen this last part of the talk on natural language, I don't think.
So which papers, researchers would you point to?
Yeah, so a couple of, I'm sorry, I'm blanking on the name, but I can send it to you after the talk if you email me. There was one that did kind of the bag of words type model. If you think of a document as a bag of word vectors, then you can distinguish, you can learn models using the MMD as a notion to learn a classifier or whatever. Right. I'm blanking on one of them. Another was using Wasserstein for that from Kilian Weinberger and Matt Kusner were two of the authors. Right. And there's some testing type stuff on that also, yeah.
So more simple language models.
Yes, I haven't. Also, I think there's been a little bit of work on. I'm sorry. I think there is stuff out there, but I don't know it off the top of my head. Sorry.
Awesome. Thank you so much.
Sure. Can we go to this side first, maybe?
Hi. Thanks for the talk. I was very interested. I'm curious about this from the perspective of testing statistical software. I wrote a sampler for something. I know what it's supposed to be producing. How do I know whether it actually is producing or there has a bug?
Yep.
So in that setting, I have a huge amount of control over N. How many samples I draw, but I don't want to draw too many because it's a test suite, everybody's running it every day. So is there any way to estimate what the power actually is?
Yes, so the expression that we gave there, the asymptotic expression, is, so you can get, I only gave the asymptotic leading order term for the variance, but you can actually get an unbiased estimator for the variance at any sample size. And that expression for the power, it does rely on some asymptotics, but depending on the kernel choice, it should be okay at moderate sample sizes. So this isn't something I've seen evaluated in detail, but I think if you just took that full expression, not just the ratio, but the full thing with the normal CDF around it, I think it should be an okay estimate of the power at moderate sample sizes. Another related thing to that is there's a paper that Arthur did a couple years ago for doing that specifically for if you have you have an MCMC type sampler, so you don't actually quite have IID samples, but there's some autocorrelation in them, using the wild bootstrap to account for that time variation there, if that's relevant.
Yeah. Thanks.
Two kind of related questions. How easy do you think it would be to use your method for time series? So it's just looking at the changes in distribution of a non-stationary time series. And also, one of the things that people are always talking about in production systems is when should we retrain our model? How well do you, how would you go about using your method to say, to answer, is the model still distribution, the model expects the same as what's actually being presented to it?
Yeah, so for the first part, for change points in time series, you could do this in a sliding window. One issue is then you're going to have relatively small n, and so it's going to be hard to learn a good kernel for every sliding window. So actually there was an iClear paper, I think, this last iClear, about that by Barnabash Poksos. In terms of the second one, I don't think I've seen practical work on that, but I know some people, I know of a startup doing something kind of like that. I think this kind of method is definitely applicable to, is my training set that I trained my model on different from what I'm actually seeing in the world right now, for sure.
Thank you.
to.
Yeah, thank you for the interesting talk. Looking at the witness function of your MMD, it seems to bear some resemblance to the latent function of a GP classifier with the same kernel. And there we pick sigma and kernels by doing empirical Bayes and other things like that. Could you comment a little bit on this connection? Is there...
So there is actually a connection, a very direct connection, which is that the witness function of the MMD is... Let me make sure I'm saying this right. If you take a Gaussian process with that same kernel and you draw functions from it, they don't actually live in this RKHS. But if you take like the EPF minus EPQ, where F is drawn from a GP prior with the same kernel, you actually get the same value out as the MMD. So there's a very direct Gaussian process interpretation. There's a paper by Morinobu Kanagawa and Dino Sejdinovic, and I think some others that talks about that in detail. In terms of empirical Bayes stuff, there might be, I don't know offhand of whether that kind of approach is applicable here. It might be interesting to think about.
Thank you.
Yeah, I think maybe, sorry, for time purposes, you can ask again at the end. Sorry.
So far you have seen many interpretable approaches for distribution comparison, and I would like to continue from where Dougal left off, and I would like to introduce you to another linear time to sample test that is also interpretable. So to introduce this idea, let's recall the MMD witness function from part 1 that Arthur introduced to you. So again, you have seen this before. This is the witness function, right, in black. So, and also recall that the MMD is just the norm of this witness function. Now, to get interpretability, so we are going to do something slightly different here. So instead of taking the norm, what you can do is you can take the witness function and first notice that the witness function is 0 function if and only if P is Q. Right? You have seen this already. And it also turns out that the magnitude of the witness function indicates the difference of P and Q. And so what we can do is we can actually square the witness function, like so. So you get squared witness, and just evaluate this squared witness function at some locations, which I will denote by V, so V1 to Vj, okay? So these are what we call test locations. So these J test locations live in the same domain as your data. And later we will optimize these J locations to give interpretability. They will tell where P and Q differ. But for now, let's pretend that they are given. And let me tell you the statistic first. So if you do this, given some test locations, you simply evaluate the witness function, the squared witness function, and take the average. That gives you a new statistic. It's called the UME, the unnormalized mean embedding statistic. So now, the first question is, what can you say about this statistic? And it turns out that this UME is 0 if and only if P is Q. It has the same property as MMD, which is 0 if and only if P is Q. It is a proper distance under some technical conditions. Like the first one is just the kernel has to be nice, it has to be characteristic, and it has to be real analytic, meaning that it has to be very smooth. And second, the test locations have to be drawn from a distribution that covers the whole domain. So if these two conditions hold, then it is 0 if and only if P is Q. And so the key takeaway from this is that simply evaluating the squared witness function is enough to detect a difference. And one good thing about this approach is that it is extremely fast. So look at the top line here. So there are j terms. Each term can be estimated in big O of n because you just need to take the average. But there are j terms, so in total is big O of jn. And j is a constant. It's going to be less than 10 in practice. So now, remember from part 2 that Dougal told you that to do the test, we need to know the null distribution. So it turns out that the null distribution of UME is quite complicated. It turns out to follow a weighted sum of correlated chi-squares. You can actually see it. It's not difficult to see. So there are j terms, and all the terms carry the two sets of samples. So they are correlated, right? And there's no closed form expression for this distribution. So one thing we can do is that we can modify the statistic just a little bit so that we can get a nicer null distribution. Oh, actually before that, of course you can do permutation test. You can always do permutation test. But since this test runs in linear time, presumably you might want to run this test on a large data set. And if you do permutation testing on a large data set, then it may take time. And so ideally, we want to get some kind of closed form expression for the null distribution. And to do so, we are going to modify the statistic just a little bit. So the idea is to decorrelate the j terms in the sum. So turns out that the UME squared can be written as self-inner product of a vector t, where t is j-dimensional. So each coordinate of t corresponds to one test location. Now, so the idea is to introduce this covariance matrix, which is j by j. Consider the inverse covariance and consider this quadratic form. So instead of t transpose t, we now have t transpose and c inverse and t. And notice that t and c both depend on the samples, and all the samples on the kernel and the test locations. And this new statistic is called the normalized ME statistic, or NME. And the runtime complexity of this is still linear in n. So it's jdn here, but it's cubic in j because of the inverse of j by j matrix. And t and c can be estimated easily. Okay, so now that we changed the statistic, so what can we say about this NME? Turns out that we still have nice properties. So as n goes to infinity, as the sample size goes to infinity, if p is the same as q, then this NME statistic follows chi-square distribution, the normal chi-square distribution, not a weighted sum of correlated chi-squares. So meaning that you can get the threshold quite easily, because 1 minus alpha quantile over chi-square is very easy to get. And second, if p is not q, the test power goes to 1 as n goes to infinity. So these are very desirable properties of a test. And further, one can choose the test locations V's, V1 to Vj, by maximizing the statistic itself, the NME square. If you do this, it will maximize the test power. So this is one nice property of the NME. So in general, it is not true to maximize. So when you take this test statistic and you maximize it, it may not give you the maximum test power. Okay, but it is true for this case. And so once you maximize this, once you optimize the test locations by maximizing the statistic itself, the test locations V1 to Vj's are interpretable, and they actually indicate where P and Q differ. So let me show you one example. Well, let's just consider this toy example, 2D example. Here, let's consider just one location, so J is 1, and so score here is just the test statistic NME as a function of V, the test location. Okay, remember the test location lives in the same domain, which is 2D space in this case. So here I can use this score function to evaluate the score at any location of my choice. For example, if I evaluate here in the middle, I get a score close to 0. So 0 means it's not really distinguishable, right? So because, well, blue and red points highly overlap in the middle. But if I evaluate the score here, it's slightly higher. Here is even higher, and in fact, the highest point is here on the right. So this point indicates the region that reveals where P and Q differ most. And by using this V, this particular location with the NME, it will maximize the probability of detecting the differences between P and Q, or maximizing the power. So okay, let's see a real example. So here, P is a distribution of faces showing positive emotions, and Q is a distribution of faces showing negative emotions like afraid, angry, disgusted. And here in this case, we know that H1 is true. The alternative is true. So P is not Q. Okay. And so here, what I'm showing you is the test power or the rejection rate. So in this case, the higher the better, because we should reject the null in this case. And no optimization means it's the NME without optimizing for the test location. I just pick randomly, pick one image randomly from the data set and use as V. So we get 60% of the test power. But if we do the optimization, turns out we can get maximum power. So the power increases a lot with the optimization. And in fact, it has the same power as the MMD, which runs in quadratic time. But the NME runs in linear time. And further, as discussed, NME can produce V, right, the test location. So in this case, I just run like straight gradient ascent, because we want to maximize, and I get this kind of location. Remember again that V lives in the same, lives in the data domain, right? In this case, this is the pixel space. It's supposed to be a face. If I overlay this, it's a face now. So here, you can actually take this V and interpret where P and Q differ. In this case, it shows that P and Q differ around this region, right? Like at the nose area and smile lines, because these are the regions that you use to kind of show the emotions, right? So the UME test can actually be extended to a model comparison. So here, P and Q are two implicit models, could be GAN models, and R is the real distribution, the distribution that generates your data set. And the goal is to decide whether P or Q is closer to R, as measured by the UME. Okay? So essentially, this is a model comparison problem, and it can be formulated like so. So we observe three sets. It's two sets of samples drawn from the two candidate models, and one set does the real observations. And we want to test the following hypotheses. The null hypothesis says that P is closer to R as measured by the UME than Q is to R. So if P is closer, that means P is better according to the UME. And the alternative hypothesis says otherwise. It says Q is better. Okay? And so once you formulate it in this way, the test statistic is quite natural. It's just the difference of the two UME estimates denoted by S hat here. And the idea is the same as before. So we need to derive the null distribution, the alternative distribution, and so on. It turns out that in this case, the null distribution is asymptotically Gaussian. The alternative distribution is also asymptotically Gaussian. It's very simple. And we can get a test threshold and so on. Further, we can also optimize the set of test locations V. And in this case, the semantic of V changes slightly. Now, the optimized locations show where Q is better than P in this case. So let me show you one example. Okay, so say here we are given two GAN models trained on MNIST. So Q is LS GAN, least squares GAN, and P is the original GAN by Goodfellow and colleagues. So what we can do here is, so these are our two candidate models. R is the set of real MNIST images. What we can do is we can prepare 10 candidate sets of test locations. Okay, so there will be 10 candidates for this set of V's. Okay, so the first one, so each set contains digits of the same type. For example, the first set contains only digits of 0. The second one contains digits of 1, and so on. And then we can evaluate we can derive the same. Remember in Dougal's part, in part 2, where he talked about the ratio, the MMD divided by the standard deviation under the alternative distribution. That is the power objective, right? The objective function that you use to maximize the test power. It turns out you can do the same for this relative UME test as well, and you get some kind of ratio as well. And now we can actually take that ratio and evaluate the ratio at these 10 sets of test locations, right? So we get 10 numbers, but we repeat multiple times, multiple trials, so we get 10 histograms. And this is what we get. So the 10 histograms are shown as 10 box plots. And so the power criterion just means the ratio, which can be negative in this case. And one property of this test is that if the power criterion is positive, it actually means that Q is better as measured around the region specified by the test locations. So here, number 1 means so let's consider this 1 here. So it says that the power criterion is positive, so it means Q is better in the region around digits 1. So you can see by yourself if 1s from Q are better than 1s from P. Another, okay, say digit 3 here, it's negative, so it means P is better around the region specified by the test locations 3, right? So 3 from P here at the bottom are better better than 3 from Q. So here, better just means closer to the true MNIST digits as measured by the UME. And here, so we use the Gaussian kernel, or I guess exponentiated quadratic kernel, on top of features from a CNN classifier. Okay, so this is, so I would like to move on to the last part of the tutorial, which is on testing explicit models with kernel Stein discrepancy. So far, this is the setting so far, right? It's 2-sample testing, where the 2 underlying distributions are represented by 2 sets of samples. But in this part, P is going to be explicit. So P will be an explicit density function known up to the normalizer. And for example, P could be a restricted Boltzmann machine, say, for example. And this setting is known in statistics as goodness of fit testing, because we are testing the goodness of fit of the model P on the data drawn from Q, and Q is unknown. Okay, and importantly, we don't have sample from P. Okay, so we have a set of samples and an explicit density function. Okay. Okay, so what can we do under this setting? So recall the IPM form of MMD from part 1, integral probability metric that you have seen. So what is wrong with this formulation? So one difficulty is the second term here, the second expectation. So it turns out that it's usually difficult to get the expectation in the second term, because this is an expectation under the distribution P, and we don't have sample from P. Remember, we have explicit model. And in practice, the model is going to be complicated, like, for example, a restricted Boltzmann machine. Like, probably you can't get exact expectation in the second term. And second problem is, okay, you might say, okay, why don't you just sample from P? Well, you can do that, but usually it's also difficult to sample from P, right? You may need to run MCMC. And in fact, more importantly, you don't want to represent P with a collection of points. So having an explicit density function is way more informative than having a set of samples. So ideally, you want to make use of P directly without sampling, right? And so somehow we need to deal with the second term. So the first term, the first term is fine because we have samples from Q. We can replace this E with the average over the samples. So what can we do? So here's an idea due to Stein. The idea is very simple. Well, we just get rid of the second term. But how do we do this? Well, we will introduce a so-called Stein operator, okay, denoted by TP. This Stein operator is an operator that takes in a function f and produces a new function. And the operator looks like this. Okay? It involves the derivative of the product of f and p, and there's also 1 over p here. And this operator is defined in such a way that the expectation under p is always 0 under some boundary conditions. So meaning that the second term here is always 0. So to see this is actually, the proof is very short. To see this, okay, let me give you a proof. Okay, so the first line, this is just by definition, this is expectation of the Stein operator. So the thing in the square bracket here is just the Stein operator. Now we see that p cancels, right? Now we are left with this integral of the derivative, but by the fundamental theorem of calculus, this just gives us the thing in the bracket, which is the product of f and p from -infinity to infinity. And this is 0 under our boundary conditions. We assume that the product of f and p is 0 as x goes to infinity or goes to negative infinity, which is actually true in many cases. If you say imagine that p is a Gaussian, Gaussian has an exponentially decaying tail. So if f is sufficiently well behaved, meaning that f doesn't blow up, then the product will be 0, right? This is just kind of intuition. Okay, so now we know that the second term is always 0. And so it turns out the kernel Stein discrepancy is defined exactly this, right? It's an IPM with modified it's a modified form of IPM with this Stein operator TP, right? And as we know, the second term is always 0, so we can drop it, and we are left with only the expectation and the Q in the first term. And remember from the first part of the tutorial in the MMD, remember the picture with sort of 2D picture of unit ball when we derive the witness function? It's actually the same argument here. It turns out that the supremum can be obtained in closed form. And it turns out that the supremum is given by the norm of a function g, where g looks like this, okay? And this g has a name, it's called the Stein witness function. It's an analog of the MMD witness function that you saw earlier, but this is a Stein witness function because it depends on the Stein operator. It explicitly depends on the density p here. And we will make use of this later for interpretability. Okay, but for now, so how do we compute this? How do we compute this norm of G? Okay, yeah. Another thing I want to note is that look at the form here. There's P in the numerator, and there's also P in the denominator. That actually means that the normalizer cancels. So meaning that this KSD doesn't depend on the normalizer. So you can just apply this without having to know the normalizer. Okay, so how do we compute this norm of G? It turns out that the squared KSD, squared kernel Stein discrepancy, can be written as in this form with double expectations of a function h, where h looks like this long expression here, where SP is just the score function. It's the gradient of the log density of P. Okay, so this h function depends on the score function of P. It depends on the kernel K. It also depends on the derivative of the kernel. Okay, and of course, KSD also has the usual expected property, which is that under appropriate technical conditions, so you saw earlier that we need one boundary condition. We also have a condition on the kernel. So the kernel has to be nice in some sense. In this case, it has to be C0 universal. So under some appropriate technical conditions, the KSD is 0 if and only if P is Q, meaning that it is also a proper discrepancy measure. So, okay, so how do we actually run the test? So look at this form here in the first line. Obviously, so in practice, remember that we observe one set of samples from Q, so we get Y1 to Yn. We can simply just replace the population expectation here with an empirical average, and you are done. That is an estimator shown here. This is it. This is KSD hat. Okay. And so this is your test statistic for goodness of fit testing. And the complexity of this is d square n square. So n square can be easily seen because you have double sums here. D square comes from taking the gradient. And it turns out that the asymptotic distributions are very similar to the MMD case. Under the null hypothesis, when P is equal to Q, this KSD hat follows an infinite weighted sum of chi-squared variables that Dougal also showed you in part 2. Under the alternative, so when P is not Q, the KSD goes to asymptotic normal. So it asymptotically follows a normal distribution. Now, remember in the case of MMD, to do the test, we don't actually estimate the exact form of the null distribution, but rather we rely on permutation testing, remember? But here, interestingly, we cannot do permutation testing. And the reason is because there's nothing to permute. We have only one set of samples. There's nothing to permute, right? And so we have to do something different. And in practice, we rely on something called wide bootstrapping, which is just a way to simulate a null distribution by sort of randomly introducing random weights into the sum here, which I don't have time to go into these details, but it's not so difficult. So please check the paper or come or talk to me after. Okay, so that is the KSD. Now, so now I would like to show you the last test in this tutorial, which is a linear time version of the KSD. Okay, and so remember the Stein witness function G, right? Here, G. It turns out that it also has the same property as the MMD witness function, which is that it is going to be a zero function if and only if P is Q, right? So in this, for example, take a look at this picture here, where P and Q are exactly the same. So G is the zero function. Now, if P and Q are different, then G will no longer be a zero function. And in fact, if P and Q differ even more, then the magnitude of G gets even larger. This actually suggests that we can also just take G and evaluate at some test locations. So remember this familiar idea from UME is exactly the same idea here, actually. So one can also take this Stein witness function, G, and evaluate at some finitely many test locations, V1 to Vj, where these are just points in the data domain. And again, so we can also optimize these points, and later these points will show you where P and Q differ. Okay, so if you do this, it's known as the finite set Stein discrepancy, or FSSD. So the exact equation is shown here. So basically, it just says that take G, evaluate at J locations, and take the average. And in fact, the FSSD is to KSD as UME is to MMD. It's a linear time extension of KSD, just as in UME, which is a linear time extension of MMD. There's a theorem. So assume the same conditions as in KSD, and further assume that the kernel is real analytic, meaning that very smooth, infinitely differentiable. And also assume that the V, the test locations, are drawn from a distribution that covers the whole domain. Then it turns out that the FSSD is also a proper discrepancy measure, meaning that it is zero if and only if P is Q. So how do we do the test? Well, I mean, so far you have seen so many tests already. I guess you can already guess the behavior of the squared FSSD, it turns out to have very similar behavior as in MMD and DKSD. So this is the behavior. So under the null, so when P is Q, the FSSD follows a finite weighted sum of chi-square variables. So the difference with MMD is that instead of an infinite sum, we have finite sum. That is the only difference. Under the alternative, when P is not Q, this statistic FSSD asymptotically follows a Gaussian. And one difference, though, is that, so in the case of MMD, we cannot estimate the weights easily, and we will rely on permutation. In this case, we have a finite sum, meaning that we have finitely many weights, and it turns out we can actually estimate the weights. And the weights are given by eigenvalues of a dj by dj covariance matrix. And so once we get the weights, we can actually simulate the null distribution shown in green here by just repeatedly sampling from this distribution given by weighted sum of chi-squared variables. And we can get the histogram, and we can estimate the 1 minus alpha quantile to do the test. Okay, so now remember from part 2 that we can choose the best kernel by maximizing the test power. We can do exact same thing here. So if we write down the expression of the power for the FSSD, it looks very similar to the MMD because the alternative distribution is also Gaussian, and so you get sort of familiar form as in part 2, right? So the asymptotic power expression looks like this, right? Where phi is just the CDF of the standard Gaussian, and we get this kind of ratio as in MMD, but in this case it's the FSD square divided by the standard deviation under the alternative distribution of FSSD. And so we can actually find the test locations by maximizing this power expression. And we can follow the same line of reasoning, which is that for large n, the first term will dominate, right? Because it carries root n, and the second term carries 1 over root n. And so the first term dominates when n is large. So maximizing the power amounts to maximizing this ratio here. And this ratio is our sort of objective function for choosing the test locations. Okay, so to show you an example, so I'm going to consider this problem, the Chicago crime example. So here's the map of Chicago. We are given a data set shown in blue, where each point represents a latitude-longitude coordinate of one robbery event in Chicago in 2016. And the goal here is to model the spatial density of the crimes, the robbery events, with some models, Gaussian mixtures, say. And let's say that we are given this model. This is our P, right? P is a 2-component Gaussian mixture. And the goal is to do goodness of fit testing of this P. Now, we can run our procedure, right? We can consider the power criterion, the ratio function, as our score function, and show this score function. So here, dark color indicates high mismatch, so it's high score, high mismatch between P and Q. And you can see that it's quite dark in this area here on the right. And in fact, if you do the maximization of the score function, so find the best point with the highest test power, you get here. And the reason it is here is because, well, because that is in the lake, and there's no robbery in the lake. But if you look at the model says that there should be something, right? It puts quite a lot of probability mass here on the right. So there's sort of, so more technically, the model is a Gaussian mixture. It says that the tail should have exponentially decaying tail, right? So this is the profile of a Gaussian, but it doesn't. The data don't have this. The reason is because there's a sharp cut here. There's no exponentially decaying tail. So there's a tail mismatch, and therefore that is where, all right? Okay, so what about a more complicated, yeah, of course there's no robbery. So what about a more complicated model, right? So say, okay, instead of 2-component, we can consider 10-component Gaussian mixture. we can run the same procedure. We consider the score function and so on. We do the maximization. Now we get this location instead. So the reason is because now the right tail now has a better fit, right? Because of a sort of more powerful model. But still, there's still some mismatch on the left. So this approach of learning test locations allows you to interpret where the model is wrong, and it also allows you to kind of come up with a more refined or better model to fit the data. Okay, so here's the last slide of this tutorial. So I have introduced two test statistics for the goodness of fit testing. The first one was KSD, and the second one was the linear time extension, the FSSD, right? So when do we use KSD or FSSD? So remember that the KSD here, remember that KSD is given by the norm of the Stein witness function. And it turns out that KSD is good when the difference between the two distributions is spatially diffuse. So spatially diffuse means that the Stein witness function is almost zero function, is flat, but it's not quite zero function. So in that case, FSSD is not so good. It's not so good because no matter where you evaluate G, you are going to get sort of low signal, right? Because it's almost flat. Whereas if you take the norm, it will account for that. So KSD is good when the difference is spatially diffuse, whereas FSSD is good when the difference is local. So local difference means that the Stein witness is actually like spiky, so you can find the best location to evaluate and get large signal. Okay, so to conclude the tutorial, so there are three parts, right? In part one, you have seen many divergence measures. You have seen two families of divergence measures, the integral probability matrix, IPM, and the second was phi divergences or F divergences. In part two, by Dougal, you have seen hypothesis testing. You have seen how to use MMD to do two-sample testing. You have seen null distribution, the alternative distribution. Kernel design, you can put a kernel on top of extracted features from a deep net. You have seen how to choose the best kernel by maximizing the test power. And in the last part that I just covered, I introduced one linear time two-sample test, the UME test, that is also interpretable by outputting the test locations. You have seen the KSD, which is a Stein, which relies on Stein's method. You have also seen the sort of linear time extension of KSD, where you have the same notion of test locations as in UME. So if you would like to know more, please, here is a list of references, and thank you for your attention.